Hey everybody, welcome back. So today we're going to be looking at different ways that we can define the same parametrized surface, and specifically we're going to be talking about changing coordinates from one parameterization to another parameterization. And so as an example, right, and this will be sort of the main example that we look at, this is a parametrized surface. This is the upper half sphere, right? So this is just the outer shell of this upper half sphere. And it is a parametrized surface sitting in three-dimensional space, but we've got two different coordinate systems, two different coordinate systems and two different parameterizations of this surface. On the one hand, we have this function, y, which I'll call y, and it is mapping from the theta phi space into three-dimensional space, and it's given by the parameterization y of theta comma phi is equal to cosine theta sine phi, cosine phi, right? So this is our x, y, and z coordinate here in space. And our domain space, right, this is the theta phi space over here, goes as theta ranges from 0 to 2 pi, and as phi ranges from 0 up to pi over 2. And so this might look familiar, it might not, but it might look familiar as our standard spherical coordinate parameterization, right? So these functions here define or use our standard spherical coordinates, right? Specifically theta and phi. Theta is measuring our sort of angle in this direction, right? Angle out from the positive y direction, positive x direction, and circling in the xy space, while phi sort of measures our sort of height, right? Pointing from up here at phi equals 0, and then pointing down to phi equals pi over 2, right? So this is our standard spherical coordinate transformation from, say, a Calc 3 class. At the same time, we have another coordinate system, right? We can talk about this map, x of u comma v, and this is the map x of u comma v equals u comma v, comma the square root of 1 minus u squared minus v squared. So this is also mapping a set of points in a two-dimensional space, right? This is our uv plane, and it's mapping it into three-dimensional space. And specifically, our set u that we're looking at, right, our set down here, is going to be the set that is the closed unit circle, right? So this is a unit circle in UV space, and I'm also thinking of all the points inside the unit circle. And this map is just going to be the graph map, right? So this is our x-coordinate is just our u, our y-coordinate is just our v, and so then the z-coordinate is just going to be the height of this function here, the square root of 1 minus u squared minus v squared. And so this is graphing the upper hemisphere as a graph, right? Or as we might have seen it as a graph. So we have two completely valid parameterizations of the unit sphere, or the unit hemisphere. All right, now, because each of these are a valid map, right? Because this y is a valid map and this x is a valid map, we should be able to do calculations about this parameterized surface using either coordinate system, right? Either in terms of theta and phi, or in terms of u and v. And we might be interested in doing the same computation in either coordinate system, right? Maybe certain computations will be easier using this parameterization, while other computations would be easier using this parameterization. And so it's worthwhile to think about how we can translate between this coordinate space and this coordinate space. And so what I'm really talking about here is a change of coordinates, or a change of variables, translating from my theta phi space into my uv space, for example. And it turns out we can do this by creating a function that goes from this subset of R2 to this subset of R2 appropriately. And so what I'm talking about is really a map, right? And I'll call this map capital F, right? That would map a point up here, like a theta comma phi, to a point down here, right? A u comma v. And it turns out that there is such a map that does this very naturally. Let me slide up here to give us a little more space. We could talk about the map F right? This is f of theta phi equals, and then we've got cosine theta sine phi sine theta sine phi. And it turns out that this function, right, takes a point theta comma phi and maps it to an associated point u comma v, where here this coordinate is our u coordinate, right? So that would be the u coordinate. This coordinate is our v coordinate. And we get a map from a point up here to a point down here. And importantly, right, I won't necessarily prove this up here, but importantly, this rectangle gets mapped perfectly into this circle, right? And so we have a sort of opportunity to either take a parametrized surface just by considering this x function, or just considering this y function, or now taking a point up here, right, a point in this domain, and mapping it from up here down here via the function f, and then up through here via the function x. Right? And so we have that composition of functions x of f of a point phi, theta comma phi. And in fact, both the original parameterization y that just goes directly here and the composition of functions, right, x of f that maps in this route will give us the same coordinate patch. They will both give us this exact same upper hemisphere. All right, great. So we might be interested in knowing when we have different options for our coordinate systems, as we did here, whether there's a nice function that allows us to translate between coordinates nicely, right? And we might want that function to be nice in a certain way, right? We might expect that function to be continuous or differentiable. In a lot of our computations, we're taking a lot of derivatives, and we might want to understand how taking derivatives in one coordinate system might convert to or change to taking derivatives in another coordinate system, right? And so we're interested in a function f that has nice properties with respect to differentiability and with respect to covering the same coordinate patch. And that leads us to the following definition, right? We can say that if we have two different subsets of two-dimensional space, u and v, then a function mapping from one subset to the other is called a diffeomorphism if it satisfies two properties. First, the function should be a bijection. In other words, it's invertible, right? It's a one-to-one and onto function. And second, if both the original function f and the inverse function f inverse are themselves differentiable functions, right? So again, a bijection is going to be a map that maps from one subset of R2 to another, right? Just like here we have this theoretical function f mapping the rectangle down to the unit disk, right? From one subset of R2 to another. And the hope is that this is a bijection, so it's one-to-one and onto, and the function itself is differentiable with a differentiable inverse. If that is the case, then we call such a function a diffeomorphism. And if we unpack that word a little bit, right, morphism being sort of change, but diffeo meaning differentiable, a diffeomorphism is essentially a differentiable way to change one subset of R2 to another. And the idea is that we should be able to do this from one sort of domain of a coordinate patch to another. And in doing so, we can translate our computations from one coordinate space to another coordinate space. All right, so what does it mean for our function to be differentiable, right? Well, this is a function from R2 to R2, and we said that a function is differentiable if its differential can be computed. I think I actually said that backwards. If a function is differentiable, in other words, if we can take this function from R2 to R2 and successfully take derivatives, then we can create a matrix called the differential of f, right? And the differential was just a matrix that incorporated all of our different derivative information, right? And we denoted it either as capital DF or as lowercase df, but in these brackets to signify that it's matrix valued. All right, so for example, right, if we consider our function f from before, this was f of theta comma phi is cos theta sine phi comma sine theta sine phi, right? This was a function from a subset of R2, right? But we sort of denoted it as R2 with the variables theta and phi, into another subset of R2, which we denoted with the variables u comma v, right? So it's from R2, 2 coordinates, to R2, 2 coordinates. And so the differential in this case would be a 2 by 2 matrix where we would take our coordinate u and take its partial derivative with respect to theta, with respect to phi, and then we would take our coordinate v and take its partial derivative, theta, and with respect to phi. So we'd end up with this 2 by 2 matrix of partial derivatives. That's right. So if we have this matrix of partial derivatives, this will be useful in determining how our transformation, how our diffeomorphism converts variables, theta comma phi into variables u comma v. And when we go on to do computations, being able to compute this matrix will be relatively helpful. And so we can do that here, right, by noting that in this case, let's scroll just up here a little bit, by taking the variable, or by taking this derivative here, we can say that du d theta, right, would be a negative sine of theta comma sine phi. Right? And then if we go on to take the theta derivative, the phi derivative of this, we would end up with cosine of theta cosine of phi. And then for our 2 entries down here, we would end up taking first the theta derivative of the v coordinate. So that's cosine theta sine phi. And then up here, we would take the phi derivative, so that's going to be sine theta cosine phi. All right, and so we get this differential, right, this 2 by 2 matrix describing all of the partial derivatives of our coordinate functions. Now notice, because this map F is mapping from theta phi space to u v space, right, the inputs are variables thetas and phis, and as a result, our matrix has thetas and phis in them. So this is an expression that we can compute using those theta and phi variables. Specifically, at any given point, theta comma phi, in our original domain, I can compute this differential matrix, right, and get a 2 by 2 matrix that's describing what the differential looks like at that particular theta and at that particular phi. Of course, if I was looking at the inverse function, that would map u comma v space to theta comma phi space, and as a result, the variables that we would be inputting there would be u's and v's, describing how the differential behaves or what the differential looks like for that inverse function as well. Okay, so here is a sort of a schematic, right? We have our one set, which I'm calling U, right? This is sort of the equivalent of our theta phi space before. So I've got this set here, mapping into this set here. So mapping, I should say, here we have a U, and we're mapping into the space V. On the other hand, we've got our inverse function, F inverse, that's mapping from V back into U. Right? And specifically, let's say that this is mapping, or this is correlating the point Q prime over here in U space to the point Q over here in V space, right? In other words, my function f sends that point to that point, while F inverse sends that point back to that point. Given that setup, a question we can ask is, how does the matrix df, right? As a reminder, that's a 2 by 2 matrix that might have thetas and phis as variables. How does the matrix df, evaluated at the point q prime, relate to the matrix df inverse, right? That's the differential of this map, and that's using u comma v coordinates here, how does that matrix evaluated at Q relate to this matrix evaluated at Q prime? All right, so how do these two relate to each other? And it turns out, luckily enough, happily enough, that those matrices are just inverses of each other. In other words, the matrix we compute for df inverse, once I evaluate it at the point Q, is just equal to the inverse of the matrix df evaluated at the point Q prime. Right? And so how do we prove this? Well, we just have to apply our multivariable chain rule. As a reminder, the multivariable chain rule said that if you have a differential of a composition of functions, f of g, that was equal to df, that differential, times dg via matrix multiplication. So what happens if I compute the differential of my function capital F composed with my function capital F inverse? Right? So if I want to do that, I end up with d of f inverse, which is just going to be df times df inverse. And let's get the parentheses here, right? This is df times d of f inverse. Right? But at the same time, I know that f of f inverse is just the identity, right? This is what it means when we talk about a function and its inverse, is that they undo each other. So if I take f of f inverse, I should just get back to where I started. So this is the identity in R2, right? And d of the identity, right? D of the identity is just going to be the identity matrix, right? So this is just going to be the matrix 1, 0, 0, 1, the 2x2 identity matrix. So what we have, and you know, I guess if we sort of read it this way, is that df times d of f inverse is equal to the identity matrix, and so therefore d of f inverse must itself be the inverse of df. So in other words, the differential of the inverse function gives us the matrix that is the inverse matrix of df. So this is sort of a quick introduction to the idea of changing variables, computing the differential of this change of variables, and being able to convert from one variable system to another and then back.